So we're going to start today with chapter 10. So this is not part of our exam next week. So we're going to go with titrimetry. So if you what we call know about titrimetry, this is just what you've been doing in most of your lab experiments. So titrimetry is just titration. Okay. So all of you now, okay, has done titration. So what we're going to do is we're going to discuss about the concept of the titration and the different titrations that we do. Okay. So if you're going to recall the titration that we have, I think we started titration as early as what? Experiment 3. So both experiment 3 and experiment 4 are what? They are both an acid-base titration. And then when we go to experiment 5, we have the precipitation titration. And then we go with experiment 6. It's really a double indicator titration. Okay. And then the last one that we have is EDTA. So we're going to discuss the concept of that experiment that we did last week in today's class. So titration, this is just a procedure in which one substance, which we call the titrant, is carefully added to another, which we call the analyte, until complete reaction has occurred. Okay? And the quantity of titrant required for complete reaction tells how much analyte is present. So as I've told you, the basis for this reaction are the stuff that I mentioned here: acid-base, precipitation, double indicator, or EDTA. Okay, and we have another thing that you're going to do, which is redox next week. Okay, so titration is volumetric analysis. So remember, we have a gravimetric analysis based on gravity or the weight or the mass. Now, titration is based on the volume. Okay, so this is a technique in which the volume of material needed to react with the analyte is measured. Okay, so if we're going to look at the stuff that we have here, so maybe we can recall some of the terms that we use in this what we call titration. Okay, so we have here titrant. So titrant is the one that you put in your burette. So the substance added to the analyte in a reagent solution. So usually the titrant will be what? It's the one that's changing in terms of volume. It's the one whose volume that you record. That's the one wherein you have the initial volume and the final volume. Okay. Now what is constant with the titrant? Usually the one that's constant there is the concentration. You will not going to, there will be no change in the concentration of your titrant. But the one that's changing is the volume that you use until you reach the so-called equivalence point, which we're going to discuss later on. Now, the one that received the titrant is the analyte. So in the analyte, you have what? You have a constant concentration and volume. You're not going to change the volume of it. What changed when you add the titrant is the total volume. Okay? So that what does it mean? Okay? So it means that you can determine the moles of one of them by knowing the other one. So the way that we look at it, at equivalence point, the moles of the titrant should be equals to the moles of the analyte. And the equivalence point, that's the point in a titration in which the quantity of titrant is exactly sufficient for stoichiometric reaction with the analyte. Okay. Now, we seldom use equivalence point. The one that we usually use here is the so-called endpoint. But today, you're going to know the difference between the two. Okay. What else? What else that you use? What terms that you usually see in titration sequence. So usually when you have a sample, okay, that you want to analyze, usually what do you use? You only use a portion of your sample. What do we call on that? So let's say we have 100 ml of the sample that we have. What we do is we just use 25 ml. Okay, and the term that we have that a sample of your a portion of your sample is your aliquot. So those are the stuff that you can see in titration vocabulary. Now, if we're going to look at the requirements of the titration, it's listed here. The equilibrium constant must be large. Why? Why is K has to be large? Okay, because they said K depends on the value on desired precision and the concentration of the analyte. And typically K should be at least what? 10 to the 6. If it's much higher, like 10 to the 10, it is much better. Now the question, why is the size of your equilibrium constant should be large? Anyone? Before I make a roll call, anyone wants to answer?
Is it because you like if it's a small K value and you add a little bit, you can accidentally overshoot
Now,
the
what does the K value means? What does the K value tells us? Anyone? What does the K value tells us? You're going to take the test next week, and one topic that we have there is K. So what does the K value tells us? So what does it mean, a high K value?
It means
Anyone?
it dissociates better.
Huh?
The dissociation constant, is it?
Is it dissociation constant? Okay. What does a high K value means?
The rate of the reaction is faster.
Is it something to do with the rate?
The equilibrium concentration of the products is large or big.
Okay. So the K value tells us that it's the ratio of the products over the reactant. So if you have a K value there, that means you have more products. So in that case, okay, you want at least your K value to be large, so that means the reaction is a one direction reaction. So when you have a high K, it's favored the forward reaction. Okay, so you want the reaction to be one direction. You don't want it in equilibrium. Okay, and another thing is the reaction must be fast. Why? Why do you need the reaction to be fast? Remember, practical requirements. So what's the use if it takes an hour for the reaction to take place? Okay, you want the reaction to at least produce or be complete as soon as possible, as soon as you add the titrant. This is not going to be practical. Titrating it, what you have to wait for 1 hour, and you already added. You don't know if you reach the endpoint already. Do you see the point that I'm trying to say here? Okay, and it must be possible to observe the equivalence point. And this is where we have the so-called endpoint. So endpoint is just observe equivalence point. So usually, what is our endpoint? The one that you have observed. How do you know that you reach the endpoint? Anyone?
it's usually a color change.
Okay, color change. That's the endpoint that you have. I think that's the practical thing that can guide you if you reach the endpoint. Now, if you're going to use instrumentation like a pH meter, so maybe your endpoint would be like this. So you see the sudden rise of the pH. Okay, but in all the experiments that we did, experiment 3, 4, 5, 6, and 7, all of them involve color change. Okay, now you want the endpoint to be at least near the equivalence point. Okay, so the way that you detect the endpoint here, you define this as the point in which the titration when the equivalence point is observed. So ways to detect the endpoint, as I've told you, Brian told us, the use of colored reactants or the use of formation of colors. But there are some wherein you don't need an indicator. Okay, because the next one that we have there is the indicator. So when we have a colored reactant, we can call it a self-indicator itself. So what does it mean? On its own, it will change color. So if you have permanganate, you react it with oxalic acid. So initially we have pink color. You reach the endpoint when the pink color disappears, when it becomes clear. Okay, so we also use this indicator. This is a changes color in response to the change in the reactant's concentration. So what's the indicator that you know? Example of indicator.
What about starch and iodine? Will that be an indicator?
Yes, but we don't use them for titration unless you are reacting for vitamin C and iodine. Okay, but the one that we use,
For methyl blue,
methyl blue,
phenolphthalein,
phenolphthalein. Okay, what else?
Mithril green.
Bronchosol green. Bromthymol blue, bronchosol green, methyl red, methyl orange. Okay, and what did you use this last week? What's the indicator that you used last week? The EBT. Okay, the Ergochrome black tea. Now, another thing that you can use is simple instruments. So if you took Gen Chem at Pace University, you've done this, you use a pH meter, okay, to see the sudden increase or the sudden drop of the pH as the endpoint. Okay, so if we're going to use this simple instrument, it should respond quickly, but typical equipment should be low cost. So you're going to do this, if I'm not mistaken, in 2 weeks, the next week experiment. Okay, so in the simple instrument that we have, we usually use an electrode. So how it look like? It's like this. So what happened? The electrode would typically respond to the log of the ion concentration. So you're going to do an experiment like this, experiment 11 that I'm going to move next week, and the last experiment, which is experiment 12. Okay, so there's a rearrangement of some schedule in our lab just to give parity to those who are doing the lab. So you can also use spectroscopic means. That means you look at the measurement of the absorption of light. So the good thing with this one is they can improve titration precision versus indicators. So they are much, we could say, or more accurate compared to the indicators. So I don't know if you experience it, but have you seen the experience of which a drop could make a difference in the indicator, especially when you're using phenolphthalein? So the true endpoint there that is equals to equivalence point is the pink, permanent pink color. Okay, but usually you don't see it because a drop of that would make you a dark color. Now, there is an error associated in titration. We call it the titration error, and that's just the difference between the endpoint and the equivalence point, and it is a systematic error. Okay, so when you say systematic, it would be what? Too high or too low, but it is consistently in terms of error. It's not like the other one, like it's the random error. So note, it's possible to have large error or uncertainty in detection of reagent concentration by various methods without having great titration errors. Okay, so this is titration. Now, what else do we need to know about titration? So there's a definition also that is known as standardization. So standardization is also titration, but what makes it different? What makes it different from the typical titration? Anyone who wants to answer so that they can have a grade in their quiz? How is standardization different from the typical titration? It is a titration, but when we do it, okay, we call it standardization. So anyone? How is standardization different from Analyte titration? Anyone? From the word itself, you use a standard. Okay, so you do standardization when you use standard. Why do you have to use standard? Because you need to accurately determine an analyte concentration. So the titrant concentration must be well known. Okay, what's the rationale why you have to do standardization? So for instance, if you have sodium hydroxide, what's the problem with NaOH? It has this property. So anyone wants to say what this hygroscopic mean? So when you say hygroscopic,
like it absorbs moisture.
okay, so you can absorb moisture. Okay, so whenever it absorbs moisture, it's going to compromise the NaOH pellet that you weigh. So what will happen? What will happen to the concentration if you prepare the NaOH? The NaOH, the NaOH molarity would usually be what? High or low? With respect to the true value.
It'll be lower than calculated.
Okay. So when you prepare the solution, okay, the molarity that you have there, if you're going to look at it, the real value of that is lower than what you have calculated. Okay, because what you have there is, let's say, the mass. So instead of the real concentration about 1 gram, what will happen is you're going to measure it in terms of around 1.1 because it's absorbed moisture. So the best way for you to determine its concentration is to do a standardization. You react it with a standard. Okay, a primary standard. So when you say a primary standard is a high purity standard. So when you do this one, the titrant concentration can now be called standardization because you're reacting it with a standard. Okay, so many solutions cannot be prepared accurately from available standards. So what you do is you standardize them. So example that we have, peroxide. So peroxide usually, okay, it can decompose to give you water and oxygen. So how will you know the exact concentration of hydrogen peroxide? You react it with potassium permanganate. So neither compound is very stable, so there's no primary standard. So instead, your permanganate, you're going to determine by titration with oxalic acid in the standardization titration. So what do you have here? You know this concentration, you will get that concentration from that titration, and then you will titrate it with H2O2, so you get the concentration of your hydrogen peroxide. So usually you do this type of experiment 2 parts, and they usually put the first part as standardization. If I don't know, so anyone can answer what happened in experiment 5 in Chem 111. So those who have not answered yet. What happened in experiment 5? So maybe I'll make a roll call, so I can close those who are already. So what happened in experiment 5 of Gen Chem 1? Angel there?
Yeah, I'm here. I'm just trying to remember which lab that was.
That's the acidity of the vinegar. So what did you do there? Anyone who did Chem 111 at Pace University? There's 2 parts of that. Or maybe I could have a direct question. What's the standard that we use in experiment 5 of Chem 111? Anyone?
Is it NaOH?
We use NaOH, but that's not the primary standard that we use.
Oh,
So what we do is we standardize NaOH with that primary standard. Okay? It's a 3-letter acronym. Anyone? Anyone who can answer it, you can recall. Okay? So what we have there is KHP, the potassium hydrogen phthalate. So that is your primary standard. And what did we do? We standardized the NaOH on it. And then what happened? Once we standardize the NaOH with KHP in part A, we use that NaOH to react with the vinegar. So that's usually what standardization means. You have to get the concentration by reacting it with a standard. Okay? Now, there are what we call some properties that a standard would have. But the most common one is it's stable. It's a high molecular weight and a stable compound. So high molecular weight means over 100. Your KHP is around 204 grams per mole. Okay, so it's a high molecular weight and it's stable. So when you say stable, whatever happened in the environment, it will remain the same. Unlike NaOH, it's hygroscopic. So when you put it, you leave it standing, after some time, you will see it's moist. It has some moist on it because it absorbs water. Okay, so we also have this concept of direct and back titration. So in a direct titration, the titrant is added slowly to the analyte until reaching an endpoint. In the back titration, a reagent is added to the analyte in excess, and then that reagent is titrated to an endpoint. So we could just say this one, you put coins until you reach the amount that you need to purchase. In the back titration, if let's say you just need 75 cents, you put $1 and then you get back the 25 cents. In the direct titration, you keep adding coins until you reach the 75 cents. So I think that's the best way to express these two. Now, back titration, it's not commonly used, but when it is used, its main reason is get sharper endpoint. So the way that you do the back titration, you add in excess and then you back titrate. So you seldom do this, but when you do this, the main reason for that is for you to get a sharper endpoint. Now, how do we do calculations with titration. Okay, so for instance, this reaction that we have, the calcium content of urine can be determined by the following procedure. So your calcium is precipitated as calcium oxide or a calcium oxalate in basic solution. After that, you wash the precipitate with ice cold water to remove pre-oxalate. The solid is dissolved in acid, which gives Ca2 plus and oxalic acid in solution. And then the dissolved oxalic acid is heated at 60 degrees Celsius and titrated with potassium permanganate until the purple end of the following reaction is observed. So this is the stoichiometric ratio that you have. So what reaction is this? Anyone? So I can check you in your quiz for today. What type of reaction is this one? You can type it. Anyone, what type of reaction is this? Is this an acid-base reaction? Is this a complex reaction? Is this a precipitation reaction? You have to participate or else I'll give you 0 for your quiz for today. So this is what? Okay, nope.
Is it acid base?
Nope. Anyone? It's a redox reaction. Very good, Hanbo. It's a redox reaction. Why? How do we know redox reaction? Usually there's a change in the oxidation number. So if you're going to look at this, what's the change in the oxidation number? Manganese here would be what? So MnO4 minus. This should be like this. Okay. I don't know why it went up there. So if you're going to look at this, if it's an MnO4 minus, so this is +7 and this is +2. And then the other one is carbon. So this is what? 4 times -2, -8. So this is +6. No, not +6, +3. Because there's 2 of them. And this is +4. So one of them oxidized, one of them is reduced. Now, this is important because you're going to use the stoichiometric ratio here in the calculation. So now we're going to do calculations. So you have to have your calculator. So the standardization that we have, suppose that 0.3562 grams of sodium oxalate is dissolved in 250 ml volumetric plus. If 10 ml of this solution require 48.36 ml of KMnO4 solution for titration, what is the molarity of the permanganate solution? So what's the first step that we're going to do in this reaction? So we need to get the what? What do we need to get here? We need to get the concentration of your oxalate. So how are we going to do it? So 0.3562 grams. You divide it with what? Anyone? And divide it by 2.250 liters. So what's the value that I need here? Anyone?
Molar mass?
Okay, the molar mass. Very good. Okay, so the molar mass here is around 134 grams per mole. Okay. So If we have this, what's the answer that we will get? What's the unit that we will get here?
The unit is molarity, capital M.
Okay. So the unit is molarity. Okay. So what's the value? So this is a chance. Huh?
0.01.
0.01. I need the complete one.
Oh, 0.0106 mole.
Okay.
Molarity
Because
concentration.
if you're going to let this thing, so this is not the way that you do where you round it up. So the way that you have it here, 1, 2, 3, 4. Okay, 1, 2, 3, 4. So at least you need 4. But since this is not yet your final answer, you can add an additional thing. But we can start with 0.01. I think I messed up somewhere there. 0.01. This is what you get.
Yeah.
Okay. Now, this is the concentration of the oxalate. What are we going to do next? Anyone? Because this is the one that you have in your 250 ml. But as you could see here, not all of them were titrate. You only get an aliquot that is what? How many ml?
10.
10 ml. So the next thing that you're going to do is you have that concentration and then you multiply it with the 10 ml over 1,000 ml per liter. To give you what unit? What's the unit when you do the calculation? Anyone?
Moles.
I already showed it to you there. Moles. Okay. So when you multiply 10 ml divided by 1,000 with the molarity, you get the corresponding moles. And this is just 1.0633 times 10 to the -4 moles. Okay. Now, why do I need to do this? Why do I need to get the moles of the oxalate? What's the main reason why I need to do this?
Because in titration, the moles of the analyte and the titrant, there's a specific ratio.
Very good. Because what we're looking at is to look at the stoichiometric ratio of the moles of the analyte and the titrant. Okay. So what we're going to do here is I want to get the moles of the oxalate because from this I can get the moles of the permanganate. So what do I do now to get the moles of the permanganate? What will I do now?
We need to set it as a chemical equation.
Okay, so we go back to the equation that we had before. So how do we set this up? So how will I set up that I'm going to get from here to the moles of the permanganate?
You multiply it by the coefficients.
Okay, so how do I do that? What do I do here?
Could you go back to the equation one more time? The moles, I mean, the coefficient of permanganate would be on the top, and
So you have here 2 MnO4 minus and 5 oxalate. And if you're going to look at this, you have there the moles of the permanganate. And that would be equals to what? The others. Right now, only Jalen and Brian are cleared. So the others. What's the answer when I do that operation there?
(4.25 times 10 to the negative 5).
4.25
times 10 to the negative 5.
Now, are we done?
No.
Okay. Are we done with the problem?
Nope.
No. So what do we do next? Because what we have there is just the moles. But what we need to solve is molarity of the permanganate.
Isn't it just 48.36 milliliters?
Okay.
Turn into liters, and then you divide it by the moles.
Okay. So here. So what's the final answer that you will get here?
8.792 times 10 to the negative 4th.
8.792. Is that 92, Kyle?
Yeah.
Times 10 to the negative 4. So question, because this is your final answer, at least for this question, because this is not the only question that you have there. I just put it here so I can put the space there, because there's another follow-up question to that. Okay. So the follow-up questions that we have here. So what we did is just like a standardization there. So the next question that's going to be asked here is calcium in a 5 ml urine was precipitated, redissolved, and then required 16.17 ml of standard MnO4 solution. So find the concentration of your calcium. So that means you're going to use what you have here. So I think the exact number that you have here is 8.794. Try to double check, okay? Exponent negative 5 divided 0.044836. Yep, 8.794. So we need to use that. So what do we do next? putting line. Oh my God. So what do we do next? What do we do with this number, the concentration of your permanganate? Where will I use this one? Anyone? So what's the next calculation that I have here if I want to determine the amount of calcium in the urine? So you have this concentration. So the next thing that you're going to do, you're going to multiply it with this number. Why this number? Because that's the volume that you use of standard MnO4. So the way that you're going to do is divide it with 1,000. So once you have here, what do you get?
1.422 times 10 to the negative 5.
1.422 times 10 to the negative 5. Okay. So this is equals to what?
The moles of the MnO4.
The moles of MnO4. Okay. So what do we do next?
Convert it to the moles of the calcium.
Okay. So whenever we have this one, how are we going to move from that permanganate to the calcium? So we go back to the reactions that we have here. Maybe here. But are we here already? We're only on this one. So from here, we will get to take this one, which is equivalent to that one. And once we take that one, that is also equivalent to your calcium. So what will I do next here from 1.422 times 10 to the 5 moles MnO4 minus? So how will I set them up here? Anyone? The others who have not answered yet?
I think you like the first part, you would multiply it by 2/5.
Is it 2/5 still?
Or 5/2.
Okay. So
Oh, my bad.
check. Is it
You
5/2 or 2/5?
I think it's 5/2. Wait, can you go back one more time? I'm so sorry. I think it's 5/. Okay, MnO4. Can you? It's 5/2.
Okay. Since you have here 2 moles of MnO4 for every 5 moles of C2O4, 2 minus.
Yeah, and then the second part of it would be 1/1 because the coefficients for it.
So whatever you get here as the moles of your C2O4, 2 minus, that's also the moles of your calcium. So who can give me the number that you can get here? The other one, if you cannot say anything, you can put it in the chat.
I got 3.55 times 10 to the negative 5.
So 3.55
times 10 to the negative 5.
Okay. Is this the final answer?
No.
Okay. So what's the final answer? What else do you need to do?
Divide by the volume.
Volume, which is equals to what?
It should be the 5 milliliters.
Okay, so the 5 milliliters. So what you do is you're going to convert it to
Liters. Yeah.
And then you get the answer there. And that would be equals to what? Anyone?
7.11 times 10.
Okay. So John put there 20 007 James Bond. So this is the amount of your calcium 2+. So that's how you solve this titration. And they're doing it in the lab. Okay. What do you think the analysis that they do for the presence of what in our body? Anyone? Anyone who wants to make a wild guess?
Could you ask the question one more time?
Huh?
Could you repeat the question, please?
What do you think is the analysis, this analysis is being done for the presence of what in our body?
Oh, is it kidney stones, right? Calcium
Yep.
carbonate, I think. Kidney
So
stones.
it's for kidney stones. Because what's the problem when we grow old? We leach out calcium. Okay. Now, calcium, if it's going to what we call the react with phosphate, which is also present in our body, because that's our buffer, phosphate buffer, it can give you calcium phosphate. So calcium phosphate is one of the component of the stones, whether it's kidney stones, gold stones. Okay, so usually they are insoluble. So the presence of too much calcium is not good because that means you have what we call calcium being leached out. And if you're going to recall, precipitation usually happen once, okay, you are over the KSP value. So how are you going to get the KSP value? If one concentration of the component that make up the precipitate is present at high concentration. Okay, so that's just one titration calculation. Now there's another one. So this is a little bit what we call complicated than the first one. So you have here the sodium carbonate and the sodium bicarbonate mixture. Okay. So it said here a solid mixture weighing 1.37 grams contain only sodium bicarbonate and sodium carbonate required 29.11 ml of 0.7344 molar of HCl for complete titration. So these are the reactions that we have. So this is similar to your experiment 6. Okay, so this is the reaction that happened here. So for sodium carbonate, 2 HCl is needed. For every 1 mole, you need 2 moles of 2 HCl to produce 2 NaCl, water, and carbon dioxide. Now for sodium bicarbonate, you only need 1 mole of HCl. Okay, so how are we going to solve this problem? So the way that we're going to solve this problem is we're going to set. So for instance here, we're going to set, let's say, let X equals to one of them. Maybe the mass of your sodium carbonate. So if X is the mass of the sodium carbonate, what will be the mass of your sodium bicarbonate? Anyone?
It would be 1.375 minus X.
Okay, so it's 1.375 minus X. Everyone got Y? Anyone? Anyone has a question why we set this as this one? Because as it says there, it contains only sodium carbonate and sodium bicarbonate. So if X is the mass of sodium carbonate, so 1.375 minus X is the mass of the sodium bicarbonate. So what do we do next? How do we get the moles of this and the moles of this? Anyone? How do we define moles? So we define moles as mass over the molar mass. And this one is 1.375 minus X divided by its molar mass. Where do I get 105.99? Anyone?
You add the values of the composition from the periodic table.
Okay, so you just get this one, the molar mass. So for sodium carbonate, it's this. For sodium bicarbonate, it's this one. Now, what else do we need to know? What does this mean? The rest, where are you?
You can get the moles of HCl.
Okay, so this is the moles of the HCl. Or to make it what we call clear, that's the total moles. Because that's the one that you need to react both the sodium carbonate and the sodium bicarbonate. And if you're going to look at this, so this is what? 29.11 ml divided by 1,000 ml per liter and multiply it with 0.7344 moles per liter. So that is equals to what? The rest? What's the number that I got?
I got 0.0214.
Okay. Did you round it up?
Yeah.
Yeah. What's the one instead of 4?
3.
3 and then
7.
7. Is it not 8?
It's,
If you round
it's
it
7,
up?
8, so I guess 8.
Okay. So we need at least 4. Okay. So this is the moles of the HCl. Now, how are we going to put together the stuff that I wrote here? So this is the total moles of the HCl. So if we're going to look at this, these are from here. So how am I going to do it? How will I set up this relationship that is equals to this one? Anyone? So I put here the 0.02138 moles. So how will I set it up? Because one is pertaining to the mole of sodium carbonate, and the other one is the moles of the sodium bicarbonate. But the question is, how will I set up this relationship that I have here? Anyone want to get put a guess? Anyone? So no one's want to guess. So I put the 2 here, and this is understood as 1. I don't need to put the 1. Okay, why? Because based on the reaction of the total HCl that I have here, 2 of them comes from reacting with sodium carbonate, and 1 of them comes from reacting with sodium bicarbonate. Does that make sense?
Yes.
Okay, so you agree with me that I put 2 here because based on this one, there's 2 HCl for every sodium carbonate. I put 1 here because for sodium bicarbonate, there's 1 of HCl that react with it. So what I'm going to do, I'm going to replace this with what I did earlier, the thing that I have here. So if we're going to continue, so I have 2138 moles here. And then this one, that will be X divided by 105.99. Oh gosh. Why this one will be 1.37, what's that, 1.375 minus X over 84 point, what did I put there? 01. So that's the setup that I have. So what are we going to do now? We're going to solve for X. How do we do it? How do we solve for X? Anyone? So what will happen to this one? I think this will be like this. So how are you do the operation here?
Common denominator.
Okay, you have a common denominator, and the way that they do is you just what? 105.99 times 84.01. Right? So what's the common denominator between the two? Anyone?
8,904.22.
Very good. Maybe you could just do it like that. And then how are we going to put this value? So what is the 2x equivalent to?
168.02.
168.02. So that will be 168.02x plus so what do we have here? 137 points. So that will become what?
$145.74.
Okay. Divided by 4.01. And the last one here will be, it's not a plus, it should be a minus. 105.99 if I'm not mistaken. right? Because 8904 divided by that one, that's equals to that, because that we get from this times this. So what do we do now? We rearrange them. So maybe we cross multiply 0.2138 with 8904. And then we subtract it with 145.74. And on this side, we have 168.02. I really don't know why this happened. So here on this side, 168.02x minus 105.99x. So maybe I just ask you for the x.
0.7195.
0.7195. Anyone has other value? I can round it up around 0.7, what, 20? Did you get this value? The others?
Yes.
Okay. So if this is the value, so we need to get now the value of each this. So this is equivalent to what? The mass of the carbonate. So to get the mass of the bicarbonate, 1.375 minus this one. So the answer that you will get there, that's the value of the mass of the carbonate. So 1.375 minus 0.720 is equals to what? Anyone? So that you can have your quiz grade. So 0.655. So those are the values of the component that you have when you do the double indicator titration. Analyze. Although this is not in the what we call second exam. Questions so far? Question? Before we go with another type of titration. So this is the precipitation titration. So we're going to discuss it a little bit detailed. Okay. Although we could say we have done a similar precipitation titration in experiment 5, where the main objective there is to determine what's the stoichiometric ratio of the reaction, and the correct answer is 3/2. I think 3,6 sulfate and 4,2,4 potassium ferrocyanide. So if you have this precipitation titration, you look at the concentration of the analyte, the concentration of the titrant, and the KSP. They are the one that will influence the sharpness of the endpoint. Okay. So in acid-base reaction and the oxidation reduction reaction, we have to calculate the theoretical endpoint to determine the indicator to be used. Here, You can also do that, but you don't need an indicator because what happened here is the formation of precipitate. So the way that you're going to do the curve, if you're going to look at the titration curve, so in an acid and base, usually it looks like this. And we're going to discuss about that next 2 weeks because we have exam next week. So you also do it here. So here, what do we have? Either the volume of your OH, and this is the pH. But here, you can also do that in terms of px and the volume that's added. So this is the titration curve, the result of plotting px, okay? And similar to the pH, it's negative log x versus the concentration of the titrant. So the way that you're going to do it is, it's just like instead of this, you use px. And because the concentration varies many orders of the magnitude, it's most useful to plot the p function. So the main reason here is instead of writing there like 1 times 10 to the negative 14, so it's much better if you're going to write them in terms of function px. So that's the reason. In pH, instead of writing times 10 to the negative 7 times 10 to the negative 8, you just write the equivalent pH of that. So the example that we have here is silver iodide. So this type of titration is what we call Argentometric titration. So why do you think it's an Argentometric titration? Anyone? What does AG means?
Silver?
Yep. Or Latin name, Argentum. Okay. So what we're going to do here is we're going to look at how we form silver iodide precipitate. So remember, all halides are soluble except mercury, lead, and silver. So if you're going to look at this reaction, they said, is the reverse of the KSP. So if this is the reverse of the KSP, that means this is the dissociation of silver iodide. So the K for this reaction is just the reciprocal of KSP. Okay. So the value of the K that we have here is this one. So what can we say about this value? It's so large, right? So remember what we say about the K value at the beginning of this chapter. In a titration reaction, you want the K value to be large. So large K value means that the equilibrium lies to the right of the reaction. And each aliquot addition of silver ion titrant reacts virtually entirely to form silver iodide. So whenever you react it, you will see that there's a precipitate that form. Okay? Because the reaction proceeds completely. Now, if you're going to look at the titration curve that you're going to have here, typically it will exhibit 3 distinct regions for a single titrant reacting with a single analyte. So before equivalence point, at the equivalence point, and after the equivalence point. So that's what we're going to do today. How are we going to calculate the titration curve of a precipitation titration at this different region? So how are we going to do it? We're going to do it step by step. So before the equivalence point, okay, so let's say this is your burette, and then you have a receiving plus. So what do you think here? what is in this burette, or what is the titrant? Anyone? What is the titrant here? Is it the silver or the iodide? Anyone? What do you think is in the titrant? Is it the silver or the iodide ion? If you have this set up.
The iodide.
Is the iodide the one that you have there?
Yeah, because the amount of iodine is present.
Wouldn't it be silver because you're reacting it to give silver iodide?
Yep. It's the silver. Okay. So at the beginning, that's where the before the equivalence point, what happened after you add the silver ion from the titrant, from the burette, so you have the iodide here. So what happened is you form the precipitate. And if you're going to look at the p-value of the silver concentration, usually that's the amount of the silver ion that is left in the solution. And you might say, there's none. But the truth is there is something, but the value is so what? High or low? Remember, when you add the silver, they always form silver iodide. But the question that is being asked here is, what is the amount of the silver ion left in the solution? Are they so high or they're so low?
It should be super low, right? Because the
Yep.
KSP is so high.
Okay, because what happened, when you add the silver ion there, it will form silver iodide right away. You might even say, oh, there's nothing left there, but there is some left. But their value is just so low. Okay? And how do you get that thing? You know the amount of the iodide present. And from the KSP is going to be defined as what here? Like this, right? So what is the concentration of the silver ion that you have there? You know this. This is given. So how are we going to get the concentration of the silver ion? Anyone? Because you need to get there the concentration of the silver ion, and then from that, you're going to get the negative log of that to give you the P silver ion. So dividing both sides, I minus, so you get that value of silver ions. Make sense? Does that make sense?
Yeah, but would the concentration of the iodine be or iodide
It's
given?
going to be given.
Okay.
And since it is an analyte, it will not change. The concentration and the volume are given. Okay, we have a number later on. I'm just trying to show you what it happened. Now at equivalence point, what happened here? So this is where they are a stoichiometric ratio. So at equivalence point, the stoichiometric amount of silver ion as your iodide, so all has precipitated out. So what do you think is the value of your silver ion? You do the regular KSP. So what does it mean? At equivalence point, you let this as what? S. So this is S squared. So S is just the square root of KSP, and that's the concentration of both the silver ion and the iodide. So they already what? The silver ion and iodide are meeting already. Earlier, one is so high, the other one is so low. Here, they start to meet. They're already equal. And then after the equivalence point, the silver ion is now the one that is in excess. So the way that you're going to do it is just using the dilution factor to determine the concentration of your silver ion. Don't worry, we have a number on this. I'm just trying to show you how it happened. Okay, so this is what we're going to do, the number. So you have 0.1 molar of 25 ml iodide. You titrated it with 0.05 molar of silver ion. You're given the KSP here as 8.3 times 10 to the negative 17. So you are asked to calculate the concentration of a silver ion in solution after addition of 10 ml at the equivalence point and after addition of 52 ml. So if you're going to solve this problem, the first thing for you to do is get the equivalence point. How do you do that? How do you get BE? This is the stuff that you learn from Gen Chem. Anyone?
Ice table.
Is it the ice? Nope. Much simpler than that. Anyone?
See what's in excess?
C1, B1, C2, B2. And one of them you can sign as BE. So you're going to look at this value, 25 ml times 0.1, and then divide it by 0.05. And you get there the BE. And that is equals to what? If you have this value. Anyone, you have not answered yet? It's a simple calculation. What do you get? 50. Very good. Okay. So that's 50 ml. So this will be your guide. When I say this will be your guide, what do I mean by that? So anything before 50 is before equivalence point. Anything after 50 is after equivalence point. That's why the first thing that you do if we have a precipitation titration like this is to get the equivalence volume. Okay. So that means you have 50 ml here. Now the question is, how are we going to answer them? So I think I have a step-by-step here. So we already did the first one. Calculate the volume of the titrant needed to reach the equilibrium. And we found out it's around 50 ml, right? So it's a C1B1 equals to C2B2. The mole ratio is 1:1. So before equivalence point, this is what we're going to do. A is for the analyte, T is for the titrant. What is the analyte here? The silver ion or the iodide ion? Anyone? Is it the silver ion or the iodide ion? If we're talking about the analyte. Hello? So what do we have here? 10 ml. So 10 ml with 50 ml, what is that? 1 pip, right? So in terms of the fraction of titrant remaining, what would be the fraction of the titrant remaining? If 1 pip of that reacts with the silver, so you have here what? 4/5? Does this make sense? Hello?
Yes.
Where did I get the 4/5 here? Because 50 ml is the one that I need for equivalence volume. But I only have 10 ml that I added. So that means whatever I have there, it's only 1 pip. And that 1 pip is the one that's going to react with the iodide. So the one that remains unreacting is 4/5. Now what's the original concentration of the analyte? So we have here 0.1. And then we said we multiply it with the original volume of solution over the total volume. What's the original solution based on this? 25, right? Divided by what? What's the total volume now? Anyone?
75.
Is it 75? We only added 10. So this is just 35 ml. Convince yourself that it's 35. Where did I get the 35? So I just added 10 ml to the 25. So that's the total volume. And after that, I get the concentration of my analyte. And that is equals to what? Anyone? What do we get? 4/5. Someone get answer. So it's equals to 0.0514. Very good. 0.05714 molar. So that is the concentration of your iodide. Now what you have near now is what's the concentration of your silver? So you get the KSP value 8.3 times 10 to the negative 17 divided by 0.05714, and that would be equals to what? What do you get? Okay, somebody answer. 1.453. And what is the P silver of that? Negative log. So this is equals to what? Anyone? What's the equivalent of the 1.453 times 10 to the negative 15. $14.84.
Is there no maximum range for
No,
the P level of anything besides hydrogen?
there's no maximum because it depends on the KSP.
Okay.
The only reason why they use this one is to simplify. So instead of writing them times 10 to the negative 15, by making it like a P, okay, it's going to give you an idea on the value that you have. But what you can say is the lower the P value, the more concentrated your ions. We can get the Pi minus also if you want. So what's the Pi? Pi minus. So negative log of 0.05714. I just want to show you how they change as you do titration. So this is equals to what? Anyone?
1.243.
So you have 1.24. This is unlike OH, the pH and the POH that will give you always 14. This is not like that. Okay? The only information that is close to you here, I don't know if you still recall your pH. If your pH value is low, you have a high H plus concentration. If your pH value is high, you have a low concentration of the H plus. Now, I want you to monitor it as we go on with the titration. So, silver ion 14.84, iodide 1.24. So what's the next thing that we do? Equivalence points. So all we need to do is get the square root of 1.3 times 10 to the negative, is that 18? 17. And that is equals to what?
$3.61 times 10 to the negative 9.
So that is equivalent to your silver ion and iodide ion. So if you're going to get the P silver ion and P iodide ion, they should be the same. And that is equals to what? Anyone? The rest? So what's negative log of that number equals to? 8.44? Okay. Now look at the value. So initially, your silver has this value. And from this concentration to this concentration. Now, does that make sense? Does it make sense that your silver ion concentration goes up while your iodide concentration goes down? Because initially, this is the concentration of your iodide. Now it's only 3.61 times 10 to the negative 9. Does that make sense? Yes or no? Does those changes in concentration make sense? The answer is yes. Why? Because you keep adding silver ion. And while you're adding silver ion, they will react with the iodide. Hence, your iodide concentration or iodide ion decreases. Okay? So that's what it means. As you add silver ions, your iodide ion will react to it. So the concentration of the silver ions that you have in the solution also increases. Now, the iodide ion, on the other hand, decreases because it's going to react with any added silver iodide. Now, what happened now if you're past the equivalence point? So all you need to do is what? The original concentration of the titrant, okay, times the volume of the excess titrant times total volume of the solution. So what does this mean? What is the excess now if we're going to look at here? So we have what? 52? 52 ml. So we only need what? 50 ml to reach the equivalence point. So if we have that, we're going to use the 0.05 because that's the original concentration of the titrant. And we multiply it with 2 over, what's the total volume of the solution now? So it will be 50 plus 52. Oh, is it? No, not 50. 25 plus 50. So you're right, 77. So that gives you 1.2 or 1.30 times 10 to the negative 3. So what do we do with that? So what's the PHE now? So negative log 1.3 times 10 to the negative 3. So this is equals to what?
2.89.
Now the question, can we get I minus here? What's the concentration now of the iodide? How are we going to get the iodide concentration? So you have the KSP there, you divide it with the silver ion. So you have there the 1.3 times 10 to the negative 17. You divide it with the 1.30 times 10 to the negative 3. So you have 1.3 exponent negative 17 divided by that one. So you have what? Around 1.0 times 10 to the 14. So Pi minus is equals to log of that around 14. Now, does that make sense? So if you're going to look at the value, we started with what? 1484, 844, and then 2.89. Now for the other one, we start with 1.24, 8.4, 4, and 14. Now, does those value make sense during the titration?
Yeah. Yeah. After, like, once you start adding it, concentration of one goes up, it reaches that equivalence point. And then after you go past that equivalence point, the concentration is much higher than the other one. So like the roles flip.
Okay. So that thing makes sense. So that's how the titration curves looks on. So the question, do you think you can answer a question like this in your third exam? Hmm? You are asked either for the titrant or the analyte. Now, there are two other problems, but I leave it up to you. Maybe one of them I'll make as an assignment. Okay. Because I need to proceed to the next one here, the other information that you can get from a precipitation titration. So what we solved is a 1:1. So there are cases when there is 1:2 stoichiometric ratio. And also this one. Okay. So this is a 1:2 stoichiometric ratio also. Okay. Now, what do we need to remember about this titration curve? I'm going to show you how they look like. In a 1:1 stoichiometric ratio of the reagents, the equivalence point is the steepest point of a curve. That's the maximum point, a slope, or it's an inflection point. Now, for the other stoichiometry, it cannot, we cannot say the curve is not symmetric about the equivalence point. And usually, if it's not 1:1, the equivalent point is not the center of the steepest section of the curve. Now, what they said here, the less soluble the product or the more insoluble the product is, the sharper is the curve around the equivalence point. So this is how it looks like. So what does it mean here? Okay. So this one, that's your equivalence point. So that's where you have the so-called maximum point slope and an inflection point. So that's a maximum slope that you have. And the statement that you have here, the less soluble the product, the sharper the curve. So I want you to look at this value here, compare it with this one, compare it with this one. So the one that is 10 to the 17, it's from here. The one from the 13, it's from here. And the one with the -10, it's just here. So when you say sharper, it means distinct. You can see it right away. So the more insoluble the material is, the more sharp or the sharper is the equivalence point. Now, you can do what we call titration of a mixture here. So if I'm going to ask you, which will precipitate first? Silver iodide or silver chloride? Anyone? Or maybe all of you, round table, either AgI or AgCl in the chat. Which precipitate first? Please put your answer in the chat. AgI or AgCl? Which precipitates first? Hello? Make sure you know why it's AGI, not because the first one put it, it's AGI. Because the next question that I ask is why AGI? You cannot give me the reason because the first student said it's AGI. Why AGI? Anyone?
Because it's
Why AGI?
well, it's answered in the chat. Never mind.
Huh?
Oh, I was gonna say because it precipitates at a lower concentration because it reaches.
Okay. What else? What's the basis? There's another basis why AGI. You learn it in Gen Chem, and I repeat it in or what we call the discussion on chapter 6, which is part of your exam next week. Why is AGI? Anyone who wants to volunteer to save the others?
Because the KSP of iodide is smaller than that of Cl.
Very good. Okay. The KSP is lower compared to the chloride. And if the KSP is lower than if the KSP is lower, most likely it will precipitate first. That's the rational answer to that question. And if you're going to look at this, when you're doing a titration, okay, wherein your sample contains a chloride and an iodide, so this is how it will look like. So the BE1 that you have here, this portion here, that's where all the iodide precipitate. And then you add additional volume here. That's where your chloride precipitate. Okay? Now, as I have told you, what we have discussed is all about Argentometric titration. And in an Argentometric titration, you titrate it with silver ion. So silver is always the one that is in your titrant. Okay, and endpoint detection relies on either the electrodes or the indicator. Now there are two types. There are several types of this, what we call Argentometric titration. One, we have the Boneheart, and the other one's the Fayhans. So in the Boneheart, you form a colored complex at the endpoint. In the Fayhans, on the other hand, there's an absorption of the colored indicator on the precipitate at the endpoint. So the Fayhans would use anionic dyes. Okay, so what happened to these anionic dyes? They're attracted to the positively charged particle produced immediately after the endpoint, and the absorption changes color the dye. The absorption changes the color of the dye. So what happened here? There's a color change wherein the difluorescence greenish yellow in solution becomes pink when absorbs on silver chloride. So if we're going to look at how these two methods are what we could determine. So in the Boneheart method, you have the thiocyanate. Okay. Are you familiar with this? What is this? Lawrence. I'm going to call those who are my students in 112. What is the FESCN? So if you're my student before in Gen Chem 2, you prepare. What color usually this form?
Is it the purple?
The purple? Cesar, what color do you have there?
I think it was either purple or yellow. I don't know.
Okay, Samantha. So those who are not my former students, you prepare because they my former students cannot answer it. What color is FESCN2 plus? Samantha.
Was it like a red-ish color?
Very good.
Yeah.
That's the blood red. That's the one that's done using the during the experiment on chemical equilibrium. So usually it's a blood red complex. Okay, so what happened? When you do the Boneheart equation, okay, you use your thiocyanate there as the indicator. So it is an indicator with the FeSCN. So if FeSCN is present there, your solution will be what? As I have told you, blood red. Okay? Now, once the solution is complete, what happened? The SCN minus will react with the silver ion. Okay? So, when the reaction is already complete, it will still remain red. So the way that we're going to look at here, just put this one, the Boneheart. So we use it to determine the amount of the silver ion. So often it is used in the back titration. So this is the application of the back titration. So why you use that in back titration, you want to find the unreacted amount of the silver nitrate. So your Fe3 plus there is your indicator. Why? So this is the reaction that you have. So when they react, they will form a solid. Now what happened? Once this is gone, and you still have SCN minus, and you have the presence of Fe3 plus, what will happen? Since there's no more silver ions to react with SCN minus, your SCN minus will react with the Fe3 plus. And when that happens, you form the blood red color. And that signals the endpoint. Because that means during that time, there's no more silver to precipitate the thiocyanate. So what happened? You form the red blood solution, which means all silver ions are already used up. So you form the red one because that is already Fe3 plus that is present. So that's the concept that you have there for the Boneheart. Now for the Fahans, this is the fluorescence that you use. Okay? And usually they said they use it for chloride analysis. So if we're going to look at the Fahans, they use this absorption indicator to find the endpoint of a direct titration of an ion with the standard silver nitrate. So the common indicator that you have there for AgCl is dichlorofluorescein. So this is greenish yellow in solution, but turns pink when absorbed into silver chloride. Now the pH of the reaction must be controlled because the indicator is a weak acid and must be present in its ionic form. So the way it happened, so before the equivalence point, you have excess chloride ion there, and you have there the indicator. And if you have the excess silver ion, what will happen here? So you form into these color changes after the equivalence point. So when the charge indicator is absorbed onto the oppositely charged surface of the precipitate. So this is what happened. Okay. Now there are a lot of applications of this silver analysis. So for the Boneheart, they use it to remove this thing. And then for the Fahans, they use also the same materials as that one. So those are the applications. They still use this until the present time. And this is where we end the silver titration, because the next thing that we're going to do is the Edta, but I'm going to need a 5-minute break before we continue on this. Okay, so let's take a break. 5 minutes. So what time is it now in my clock? So clock now is, I cannot find my clock. 10:52. So let's resume after 5 minutes for the break. Okay. Okay. So this is a complexymetric concept. So the way that you have here, So metal chelate complexes. So as you can see here, you know what the metal is. And you may ask yourself, what's a chelate? So the chelate is the Edta that we use, okay? Or the way that they do it is a ligand. So when we have these complexes, this is any reagent which reacts with an analyte in a known ratio and with a very high or large equilibrium constant can potentially use. So you have metal here reacting with the chelate to give you the metal ligand complex. So that's your EDTA. Now the type of titrations that we have there is complexation titration. Why? Because you form here a complex. So this is based on the reaction of a metal ion with a chemical reagent to form a metal ligand complex. Now we could say it's a Lewis acid base titration, okay, because your metal acts as a Lewis acid or an electron pair acceptor, and the ligand act as a Lewis base, an electron pair donor. Okay, so the material that we have there, the one that we use for complexation titration, are usually called chelating agents. Okay, Edta is just one of them. There are a lot of other stuff that they have. So this is the Edta. And Edta is just short for ethylene diamine tetraacetic acid. So ethylene diamine tetraacetic acid. So that's the acronym for, the meaning of EDTA. Ethylene, that's E, diamine, D, tetraacetic, and then acid. Now, there are other chelating agents. So usually, most of the chelating agents, they have the N and the O. Okay, and it has something to do with the electron pairs that we have. So if you remember, N would have what? Like this, while O would have 2 electron pairs. So there, that electron pair, that's the one that they donate to the metal. That's the site of the chelation. And the way that they look at this Edta, it's based on the Kf value. Kf is something to do with complex ion formation, the formation constant. And if you recall in your Gen Chem 2, Kf is very unusual because they have a very high value. KSP, Ka, Kb, all of them are to the negative, but Kf, that's the only one that is to the positive. Okay? So, the way that they look at here, how do you interpret this value here? 8 times 10 to the 9, 4 times 10 to the 9. So, which is a strong complex between the two? Anyone? Is it the ethylene diamine or the methyl amine? Based on the value that we're given here. So here it says here, this has a higher value compared to this one, just twice. So the interpretation there is the 2 ethylene diamine molecules binds tighter than the methylamine molecules. So that's another way of interpreting what Kf value means. Higher KSP means more soluble, Higher Ka or higher Kb means strong, weak acid, or strong, weak base, respectively. Now, in the Edta titrations, usually we have this chelate effect. So as I've told you, how does your metal bind with your chelating agent? So usually, electron pairs of your oxygen or nitrogen. Okay? So you can have a multidentate ligand or a monodentate ligand. So what is a multidentate? More than 1 free electron pair. Monodentate, you only have 1 pair of free electrons. So The example that we can have here is, I'm not sure if you're familiar with the antibody. So multidentate ligand that binds radioactive metal attached to a monoclonal antibody. So antibody, that's the one that you develop when you are exposed to a particular stuff. So they're hoping that we can develop antibody when we are exposed to this COVID or the SARS-CoV virus, because that's the only way you can develop some sort of a vaccine, but they have not done it successfully yet. So this is the structure of the EDTA. And based from it, you have 6 acid-base sites. Where are they? This one. So what can you say about them? From our lesson last week, they're similar to amino acid, right? They have the carboxylic N, but the carboxylic N is attached to the nitrogen, the amine N. So this is the most common chelating agent. If you have problem with metal metal intoxication in your body, usually they ask you to take Edta to remove them. Now, having 6 acid-base sites means having 6 pKa value. And look at the pKa value that they have. 0.00, 1.52, 2.61, 6.13, 10.37. So you will see there at the different pH where you remove or add your hydrogen. Okay? So Edta has 6 nitrogen and oxygen in its structure, giving it 6 free electrons. So as you could see here, the hydrogen is attached to either oxygen or nitrogen. So that's the site of the metal chelating agent interaction. And if you're going to look at the fractional composition of them, this is how it looks like. If you remember what we have last week. So one form go up while the other one go down, and then another form go up. Okay. So as you can see, at higher pH, you only have 2 forms. This one, which is dominating, and this one, which is decreasing. So since you have 6 pKa, you have 7 acid-base form. And the most basic form, that's the one which primarily acts with the ion. So this is the one that we react with ion. Now, does it make sense to you now why we have to use that given pH during the experiment? What's the pH that we use during the experiment? For those who did the lab last week, what's the exact pH that we use? pH 10. Why did we use pH 10? Anyone wants to answer? Why did we use pH 10 or basic pH? Because we want it to be in this form. Okay? So at that form, that's the only form wherein they will bind with the metal. So if we're going to look at the acidic form, so these are the fractional form that we have. So this is the basic form. But you don't need to memorize that thing one. Everything is already here. So pH 10, this is the alpha value that you have. 0.30, 0.81. So as you could say, the alpha value that we have there is dependent on the pH. Okay. So what's that alpha value? That's the fraction. So depending on the pH, you're going to use it that way. So how is the Edta complexes form? So The basic form of the Edta, which is the Y4 minus, reacts with most metal to form 1:1 complex. Other forms of Edta will also chelate metal ions. So you just assume that this is what? Calcium or magnesium. So when it reacts here, you produce this one, a metal complex. So this reaction only involves the Y4 minus, but not the other forms of your EDTA. So if you're going to recall, the concentration of your Y4 minus and the total concentration of Edta in the solutions are related as follows. Whatever the alpha value depended on the pH times the concentration of the EDTA. And you will get the concentration of your Y4 minus. So if I have this value here, what if I ask you, which one will bind more tightly? Okay, let's say I put calcium and magnesium. Where is that magnesium that we have here? Yeah. So the Edta will bind preferably with what? Calcium or magnesium? Anyone?
Calcium.
Okay, answer it in the chat. So I want to see a participation. Is it calcium or magnesium? Because you have the log Kf. So if I have an Edta solution and I have a sample that contains magnesium and calcium, which metal will Edta preferably bind? Okay, so you have the log of 10 Kf. So that means what's the Kf value for that? So how do we interpret that information that we have here? So one is 8.79 and the other one is 10.65. So which one has a higher value? So between the two, calcium is preferably bound to Edta compared to magnesium. Okay. So if you substitute here the concentration of the Edta into the Kf equation, so this is what you have. So this is the Kf value. So this is the concentration of the complex that form over the concentration of the metal times the alpha fraction at a certain pH and the concentration of the EDTA. So if pH is fixed by a buffer, then the alpha Y4 minus is a constant that can be combined with the Kf. Okay, and you will end up with getting this value here. So assume that the uncomplex Edta were all in one form. So this is with just Edta at any pH. Okay, so this is the constant. This is how the reaction would look like. So Kf is just equals to whatever's the Kf given and the alpha Y4 at any pH. So how does pH affect the Edta titration? So as I tell you, in our experiment, we use pH 10. Now what happened if we use a lower pH? So if you use a lower pH, the Kf value decreases. So for instance, at pH 2, this is the concentration of the Fe3 plus. At pH 8, this is the concentration. So what happened? What happened to the concentration there as the pH increases? The Fe3 plus concentration went down. So in order to get a complete titration, the Kf should be 10 to the 6. And Edta requires a certain minimum pH for the titration of each metal. And just like in the precipitation titration, the endpoint becomes less distinct or less sharp as pH is lowered, limiting the utility of the Edta. So see, look at here. So if you have this for information that you have here, the best pH for them, okay, to have this titration would be this one, because you see here the difference when they reach the endpoint. At lower pH, you don't see that. Okay, and if you're going to look at the pH limitation by adjusting the pH of an Edta titration, you can what we call use it for a particular metal. So look at the lower pH. Which one is effective? The Fe3 plus. But look at the higher pH that we have, the one that we use. So we have Ca2 plus and then magnesium 2 plus. So that means if you have Fe3 plus and calcium 2 plus, what do you need to do to separate them using Edta? Huh? If you have an Fe3 plus and the calcium 2 plus in the solution, what do you need to do so that the one that you will separate will just Fe3 plus and not Ca2 plus? You have to change the pH. Okay. Now, in terms of the titration curve that we have, it's the same thing as the equivalence point that we learned in precipitation titration. So we have before equivalence point, at the equivalence point, and after the equivalence point. So if you're going to look at this, before the equivalence point, the metal is in excess. After the equivalence point, the Edta is the one in excess. At equivalence point, the Edta is equals to the metal. Now the question, does that make sense? That after the equivalence point, you have large excess of Edta? The answer is yes. Okay, now the question, what is the titrant here? Is it the Edta or the metal? What is the titrant in the Edta titration? Is it the Edta or the metal? You can answer, all of you, if you want. I just want to see that you're there. So what is the titrant? Is it the EDTA or the metal? Now, the way for you to know the titrant is after the equivalence point, the one in excess is the titrant. Because the titrant is the one that you keep adding. The titrant is the one that will change the volume, change in volume. So here, the Edta is always your titrant. And you did the experiment. The one that you put in your burette is the EDTA. So that means that is the titrant. Okay. So if we're going to look at the Edta titration here, so let's try to do this thing. What is the concentration of the metal and P of metal for 50 ml of a 0.5 molar magnesium 2 plus buffered at pH 10 and titrated with 0.05 molar EDTA. When 5 ml, 50 ml, and 51 ml of EDTA is added. Okay, so if we're going to look at this one, we just follow what we did with the precipitation titration. So the first thing that we do is we determine the equivalence volume. And from here we could say 50 ml 0.05 and you have the 0.05, so B is just 50 ml, although it's already given here. Now the question is, how are we going to solve this? So 5 ml. So this is equals to what? Whatever the metals that we have here. So Mn plus. How are we going to get the concentration of their Mn plus? Maybe we can use this value here. Times 50 ml, so that is also 0.05 liters. And what else? Can we subtract it with the moles of Edta added? So that is just what? 0.05 moles per liter times 5, right? And divided by what? .050 plus 0.005. And that's the concentration of your metal. So what do you get? Anyone? 0.05 times 0.05 minus 0.05 times 0.005, 225 times 10 to the negative 2.25 times 10 to the negative 3 divided by 0.055. Did you get this? So if you're going to get the PM, that is just equals to, what do you get? Negative log of that. I get 1.39. Everybody got that? Okay. Now the second one, how do we do the one at equivalence point? So in precipitation titration, we have KSP. Here, we need to use the KF because that's the only way for you to determine the Mn plus. Okay, so we can have here Kf. So we can have whatever is the Kf that is given, and then the alpha of the Y4 plus, which is equals to, so the Mn EDTA -2 over the Mn plus times the EDTA. So what is the Kf value? I think they put the Kf value here for the EDTA. So you have the 6.2 times 10 to the 8, and then that's pH 10, so that's 0.30. So how do we get the concentration here? .0250. So we're going to use like an initial concentration minus the concentration that was produced. So I'm just going to put it like this here. So if what happened is you have Mn plus, no, not that, Mn plus EDTA, and you form EDTA, right? But the way that you're going to do it is, remember, when you are at equilibrium, this becomes the reactant, and this becomes the product. So where did I get the 0.0250? Anyone? Where did I get the 0.0250? So 50 ml divided by 1,000 times 0.05. Oh, should be 0.0 something here. So that's the concentration that formed there. So what happened? Some of them dissociate, some of them form here. That's why I end up with that one. And whatever X that you're going to get here, that's the concentration of your metal. And to give you what X here, I'm going to go straight. I get around 1.16 times 10 to the -5. Or around a PM equals to 494. Now the last one that I have here, the C, I'll go straight, but we don't have any question of this in the exam. I'm just showing you what happened to the metal as we go on, okay? We have here around 6.57 for the metal Mn plus. So what happened to the metal here if you have this value? Anyone? Does the metal concentration increase or decrease upon addition of the EDTA? So 139, 1.39, 4.36, 6.57. So what can you say about the metal concentration when you add the EDTA? They increase or decrease? Anyone? From the value that you have there, do they increase or they decrease? So since the PM decreases, that means, okay, since the PM value increases, that means your metal value decrease. Remember in the pH, the lower the pH, the more H plus. So the higher the pH, the less H plus concentration. This same thing here. Okay. So if you're going to look at the plot, this is how it looks like. And this will show you the difference now, just like the titration curve. The one that has the higher KF will be what? Sharper compared to the one with lower KF value. That's the only thing I want you to look at here. Okay. So what else the one that we need to do here? So sometimes you can titrate EDTA with the calcium, copper, and what they do is they add an ammonia buffer, which results to a dark blue solution. So a copper ammonia complex would form, and then addition of Edta, it will displace the ammonia with the corresponding color change. So this is just copper sulfate. If you add ammonia there, it will become darker. If you add EDTA, okay, what will happen is the copper will bind to it. So if you're going to look at this, between Edta and ammonia, copper would preferably bind with the EDTA because it was able to displace the ammonia that you have. So in terms of the Edta titrations that we have, so this is what we did in the laboratory. Okay, so there are 4 methods that you can use if you use the ion indicators. You can have the metal ion indicator, the mercury, the pH, and the ion selective electrode, but none of them we use in the lab. Okay, so metal ion indicator, this is a compound that changes color when it binds to a metal ion. So that's the one that we use. Similar to pH indicator, which changes the color with pH as the compound binds H+. For an Edta titration, the indicator must bind the metal ion less strongly than the EDTA. So what does it mean? So we have there the indicator. So that's the one that is bind with the magnesium. So what happened? Just like copper, ammonia, and EDTA, when you place there the Edta will displace the indicator, and the Edta will bind with the magnesium. So from a red color that is due to the magnesium that is attached to the indicator, it becomes blue, which is the color of your indicator. Okay, so that's the principle that you have there in the lab. Now the question, how are we going to do the calculations there? So usually you have what? The moles per liter of EDTA times the volume that you have in liters. So you can have the moles of your EDTA. And that also corresponds to the moles of your Mg2 plus and Ca2 plus in the first run. In the second run, that corresponds to the moles of the calcium 2 plus. What differentiate these two? So to those who did the experiment, what differentiate this and this one in terms of raw data? Anyone? To those 6 students who were there? What raw data differentiate this and this? Who are there? Jalen, right? Jennifer, Samantha, Daria, Angel, and John. Volume, right? How can you say the volume of this compared to this one? So what's the relationship with that? Because that's the only calculation that you're going to do there. You're going to determine the moles of EDTA, and whatever the moles of the EDTA, that's the moles of the mixture that you have there. That's the moles of your magnesium and calcium when you're doing part 1, and that's the moles of the calcium when you're doing part 2. So how do you relate this one? B1 is what, then B2? Which one here?
B1 is greater than.
Okay, so B1 is greater than B2. Because the way that you're going to do, for B1, you're going to get the volume, or the moles of both the magnesium and the calcium. So for each of you to identify how much magnesium and calcium moles do you have there, you go to the B2. So you're going to get this. So how do we get the moles of the magnesium 2+? So usually we could say B1 minus B2 will give you the volume of your magnesium, because this is the volume of your calcium. So that's the calculation that you have there. And then what you're going to do, whatever the moles that you get, you're going to compare it with the one in the label. Or for those who use the sample in the water fountain at pace, you're just going to report what's the value, or what's the concentration of the magnesium and the calcium that you have. Okay, so how useful is the Edta titration? As I've told you, okay, if you have problems in metal, usually that's the one that you use. So if you're going to remember aerochrome black tea, so this is before, and then the equivalence point, and then after. And you witness this, those who did the experiment. Now there are other what we call metal ion indicator, but you don't need to know them. Aerochrome black tea is already enough. And the way that you look at them is they can have different indicator color. So you have the red, blue, orange, red, blue, orange, red, violet, violet, blue. So this is depending on the pH, but the one that we have is just the red and the blue. Okay. Color of metal ion complex, wine red. So if you have a wine red, that means the metal is in complex with the indicator. So the other thing that you have is this one, a different common pH thing. Okay. So what's that stuff that can be asked here? So about EDTA. Why is it a very good chelating agent? So definition of the chelating agent. So I would say from the Edta titration, I'll just get some concept question that I have. Okay. So this ends the things that we have today, and we still have a lot of time if you want to go over some question. So the coverage for our exam next week is chapter 5 to 9. And I don't know if you went over our, don't have any open thing. I'm I'm trying to see if you have the blackboard with you. Okay, so the first thing I want to discuss is the syllabus. So there's some changes in the syllabus that I have, but it's just in terms of scheduling. So this week, as I said in the email, you're going to do experiment 9, okay? And we're going to start at 2 p.m. Is that okay? Everyone? Those who are going to be here this week? And then next week, what will happen? So instead of doing experiment 10, you're going to do experiment 11. Okay? Why? Because this week is, what do I say? Not the worst experiment, but one of the longest experiment in the course. And if I don't want to interchange this, I think the other batch is at a disadvantage compared to the other batch. So after this week, we're going to go straight with 11. Okay. Now, the one after the election, it's just preparation of standard solution. The same thing with experiment 12. That's also determination of solution or standard solution. So different concentration of your magnesium and calcium for experiment 10, and then different concentration of fluoride for experiment 12. So if you're going to look at the schedule that we have, we're only going to meet 4 more times in the lab. In the lecture, this is the only meeting that we have after today. You have a second exam next week, and then we have 2 more lecture meeting. So the acid-base titrimetry and redox titration, and then we have the electrochemistry. And then after that, we have the 3rd long exam. And I look at the syllabus, I mean at our schedule, November 23 is really our last day of meeting in the university. It's not because I want to finish the course and you enjoy your Thanksgiving. It's just that that's the schedule that was set there. Okay. So this is the remaining things that we have. So if we're going to count after today, we're going to meet 2 more for lecture and 3 more for exam. So question.
So we'll take the final exam in school, right? On campus?
No, you're going to take it, let's see. I'm going to have some reflections after maybe your second exam to prepare for your 3rd and final exam. Are you okay with the present setup with an exam? Everyone, I want to hear something.
It worked out well last time, so I think most of us are okay with it.
Because if you're okay with it, I'm okay with it. It's just as simple as that. But if you're not okay, you have to let me know. Because as much as possible, I don't want to use the respondus. Because the final exam, it might just be blackboard. And it might just be a multiple choice, or there could be a calculation, but you just submit the final answer. But I still don't want to use the respondus as much as possible. That's why you're going to be what we call time pressured and no back turning. That's the what we call compromise that I usually give to my student. Open notes, okay, but time pressure and no back turning. But if it's a respondus, it's a little bit I don't know how do you say, there's a change thing also if the respondus is being done, because you cannot have open notes if you do the respondus. But if you're okay with the setup that we have, I'm fine also. That's the reason why I don't total yet the first exam, because I know the record will always be there. But after the second exam, okay, I'm going to look at it and see what's the trend among you. So you're okay with, I give you what, 9 o'clock, and then I make available the Blackboard maybe around what, 10 or 11, and then you have a time to answer the questions that you have there. Do you want to change it, or you just want to do what we have in the first exam?
I think it's fine.
I'm okay with the setup right now. Okay. Have you looked at your score? That's the thing. Have you looked at the score? All I know is no one is failing in the course so far, so I'm okay with it. So unless you have some comment on it, then let me know now. And the thing is, the materials that you have, if we're going to look at this, so I already posted the links. Now I have to put it in the YouTube, my own personal YouTube, because as you know, after 2 weeks, the link to the Page University Zoom is not already available. But once I put it there in the YouTube, I have to make it public, because if not, you'll not be able to see it. So I think I have to what we call look at this. So all the links for the second exam is already posted there. I think I have to, this should be chapter 6. And then what else do you need to know? I also posted the answer key for the quizzes. Oh no, not the quizzes, the assignment. So if you're going to look at, there's a folder chapter, this is chapter 7. So you have here documents. So that's the Zoom session. So the documents here. So if you're going to look at this assignment and problem set, so you have here the answer that I just posted last night. And then I'm going to answer the 2 assignments answers later today, once you submit them. Okay. And I also posted here the problem set. And by Friday, you will have the answer key for those problem set. I was surprised you didn't even open the answer key for the problem set 1 last time. So I have a way to know if you visited them or not. As you could see that arrow thing, that clock thing there. So it tells me if you look at it or not. So it seems to me that the answer key, you don't open them based on the record that I have here. Okay. So question with regards to the course, with regards to me.
Can we can we go over a quick topic with the polyprotic acids and the Zwitter ions real quick?
Which one?
So specifically the assignment asking about the histidine, and we were given the pKa values.
Okay.
So we have like the 4 complex ions
Yep.
of histidine, and we're given I think 3 pKa values. Can you explain what the Zwitter ion is again, and which one of those complex ions are Zwitter ions?
So the Zwitter ion is the one wherein you have a positive and a negative sign. So usually here, if I'm not mistaken, that's the second one that has the positive and the negative sign.
Right. So in terms of because I think it was asking to determine the pH of each.
Yeah.
Yeah, that's it. That's exactly it right there. Yeah, that's the assignment.
So trying to open the other one. So the way that we have it here, so you are asked at what pH you will see, or we could say, what's the pH of the different form of the histidine species. So the way that you're going to do this is, the first one, it will act like what? A weak acid. So this one will act as a weak acid.
Mm-hmm.
The second one, okay, so once you have what we call the weak acid here, so you can get the concentration of the H plus that corresponds to that, and the pH corresponding to the H plus concentration. Now the second one, it's just the average between this and this one. So this plus this divided by 2. So whatever that pH there, that's the pH we're in. You have 0.1 of this. The third one is also the pKa2 and the pKa3. So you get the sum and then divided by 2, and you will get there the pH. So I put the thing here, look. And the last one that you have here, okay, so this will act as a base. So to get the Kb, you have to get which Ka? So you're going to get the Ka3 to get the Kb1.
Mm-hmm.
So Kw minus Ka3, you have the Kb1, and you will act this as a weak base. So you will get around a pH around 11.14 to give you the 0.1 molar histidine in the most negative form.
Okay.
Most likely you will have a question like this one.
Yeah,
if it's not in that one, maybe in the multiple choice or Blackboard portion.
Right. I read my notes wrong, so I 100% did that question wrong. But that's because I read my notes incorrectly. But I see now, I understand.
So this will be posted later this afternoon. The answer key. Yeah. How about the others? Because if I'm not mistaken, we only have 1 month. You only have 1 month with me. And your Monday morning will be okay again. (11:23). That's our last meeting. How about the others? Do you have any question?
I got a question about the mass balance and charge balance.
Okay.
Like in the homework assignment, I think it was 6.
There was a mistake there. I think the one that should be positive, I make it into a negative, but I still follow the principle on how to solve it. Trying to see where it is because everyone is what we call available. Where is it? Where is it? Oh, there. Do you see it now?
Yep, I see it.
Now, the mistake that I have, this should be a CACL plus originally, but I put it a CACL minus. So I just follow how it is there.
So for A, since calcium has a positive 2 charge, right? It has a 2.
So whatever the charge that you have there, you multiply it with the charge. So this one, that's a -1, so you multiply it only with 1, which you don't really write. But it's understood that it's about 1.
And then for part B of the mass balance.
Now, I told you the mistake that I have, that should be a plus there. But since I make it into a negative, I just put this as a negative here because the way that we do is all that contains the chloride, and on the other side, all that contains the calcium.
Okay, I get it now.
Wait, Professor, can you scroll up? I just want to see like first part of assignment. Oh. I see, thank you. Because like I got, it's not in, like it's same values, but I got like 0.0002.
Yeah, but if it's in molar, it's fine.
Yeah, oh, okay, I see. So, okay, thank you.
Because what I did, this is given in millimolar, so I just follow the one that I have here.
Yeah, okay, thank you.
The thing is, why did you change it to molar?
I'm not sure. Like I thought like it should be in molar.
Because this is the same page that I have, okay? I just put something in and then scan it. So all of this will be available to you. That's why I don't know, I don't see any reason why you're going to have a problem with the present setup that we have. Most of the mistakes that you have are usually what? Carelessness. And we cannot tolerate here in analytical chemistry the carelessness thing. Because we're dealing with numbers.
So on the test, what you want, if it said calculate the ionic strength, what you want it in the millimolar or the molar?
Whatever is given.
So if it's given millimolar, then you want it in
answer it in millimolar, yeah.
Okay.
If it's given in molar, then answer it in molar.
All right, that's all my questions. I don't know about everybody else.
So question for the others. You can email me during the week or when we meet on the lab. If you have any question, just let me know. But This answer key in the assignment will be up. I will upload it now once we're done. And then all the Zoom sessions are available in the link. I hope you try to look at it. And then what else? The problem set answer, it will be available by Friday. So we will have the calculation part that will be given to you at 9 a.m. And then starting at 10 o'clock or 10:30, you can do the Blackboard part. But 12 o'clock, everything should be done. So that means we're not going to meet next week. Okay? And I want you to read carefully the instruction, especially in the calculation part. I have not done the exam yet, but I might have to do it in a way that I'll give a lot of problems, but you'll only answer what? 6 out of 10? So you have to read carefully the instruction. Because you don't want me to grade all of them and then, let's say, you didn't you didn't read the instruction properly, and you end up answering all of them. So the grading will be whatever the score over the total score times whatever the percentage of that portion in your exam. Because as you could see, we have a lot of calculations that we did. So if you want that to be covered, then there's some instances that you have to choose some of the question that will be answered. So I have not devised a way yet how to do the calculation part. But I would just suggest read the instruction carefully. Okay? So any more question? Before we call it a day? So if none, to some, see you on Wednesday at 2 p.m. To the rest, see you in 2 weeks because we're not seeing each other this next week during the exam. And if you need to go over some calculation, just email me and the time that you can have. If that time works on me, we can meet on that set time. Okay?
Professor, can we talk after class?
Okay. Yeah, just say if you want to talk with me.
Thank you.
So the others, if none, stay safe. Okay. Have a great week ahead.